All right, now we start talking about the network performance. Any multimedia application or presentation that you are dealing with that requires data communication between two nodes defines performance requirements from the network to maintain the integrity of the presentation. This might be a real-time requirement, for example, in a video teleconferencing or streaming live video over the internet, or a static example of where movies and music are downloaded prior to being played. Networking performance is very important when it comes to delivering multimedia data because the data is normally very, very large and it needs intermedia, for example, frame rate controls for videos, and intramedia, for example, video and audio synchronization. A variety of factors can affect the packet delivery from source senders to the destination, and these usually are defined by average throughput, error rate, or latency. So let's see what throughput is and what we talk about when we're basically talking about throughput. In network communication, throughput is defined as the effective rate at which a network will send or receive data, and this is measured by the amount of bits transferred over a period of time. Throughput is a very good measure for the channel bandwidth capacity, and basically it's measured in terms of bits per second or packets per second. There are several factors that affect the throughput, and among those factors you can think of the network congestion, the bottlenecks in the network, or node failure. Network congestion and bottlenecks can occur and result in dropped packets because the intermediary routers basically buffer the data, and if the buffers get to be full when packets get into it, then some of the packets would be dropped and require resending, and that would affect the throughput of your network. The receiving node in these cases might want to detect a dropped packet and signal a source to resend it. So for example, in TCP or Transmit Control Protocol, this is what happens. Or for example, in UDP, it basically ignores the dropped packets in the interest of maintaining real-time throughput. Node failures during the connection-oriented session also result in dropped packets because its input and output lines are not actively transmitting data. Error rate or error ratio measures the total number of bits or packets that were corrupted or incorrectly received compared with the total number of transmitted bits or packets. This is measured in terms of bit error rate, or BER, or packet error rate, or PER. Data corruption can occur inadvertently due to switching problems at the lower physical layer, dropped bits and packets during the transmission, misdirected packets, packets combined together, or collisions on the same medium, and so forth. Errors can also be deliberately introduced if intermediary nodes drop packets to maintain a constant or contracted bitrate service. The receiver node should have enough information to detect the error and request retransmission if necessary. In fiber optics, BER ranges from 10 to the power minus 8 to 10 to the power minus 12, whereas in satellite-based transmission, the BER occurs in the order of 10 to the power minus 7. To help reduce the and also correct the errors, error correction codes such as CRC are also communicated for the data packets. This will allow the receiver to check whether the packet was received correctly, and if necessary, request retransmission by sending a negative acknowledgement, or NAC, back to the sender. The sender learns about errors in two ways: receiving a NAC, or non-acknowledgement, or negative acknowledgement from the receiver, or the sender times out when a positive acknowledgement is not received. The next topic that we define here that can basically show you the performance of the network is called delay or latency. The process of transmitting data packets from sender to receiver is not instantaneous and happens in a small but finite time. The delay is a very important issue to multimedia communications because it heavily impacts the real-time needs and overall design architecture of your network application. Delay, which also is called latency, is normally measured as an end-to-end delay or a round-trip delay, and is the total time required for a sender to send a packet and receive an acknowledgement from the receiver. It can be described as the sum of network delay and interface delay. Network delay is basically composed of the transmit delay and the transmission delay. Transmit delay is caused by the time needed to send data on a physical connection between a sender and receiver. Transmission delay is the time that's needed to transmit a packet through the network as a result of processing delays at the intermediary nodes to look up routing tables, to compute local routes, and also to buffer or manage the buffers. Interface delay is incurred between the time a sender is ready to begin sending and the time that the network will be ready to accept and transmit the data. This might happen due to policy imposed by congestion control mechanisms and things, for example, that we talked like leaky bucket and the token bucket in the previous video. Although latency needs attention, it can be worked around by suitable buffering strategies when latency is constant. So basically here, one way to deal with latency is to use buffers. The larger problem actually is caused if the latency itself varies during the transmission. This is known as jitter as well. Depending on how the latency varies, network traffic can be defined to be asynchronous, where there is no upper bound on the latency, synchronous, where there is a smaller bound on the latency, or isosynchronous or isochronous, where the latency is constant. It is more desirable for multimedia applications, including gaming networks, to have isochronous or even synchronous data delays, where an appropriate playout buffer at the destination can be used to resolve the latency issues. The next topic to talk about as far as the performance of your network is called quality of service. Quality of service, which also we refer to as QoS, indicates how well a network performs with multimedia applications, regardless of whether the network is conforming to the required traffics for the application. The QoS effectively defines the capacity of a network to provide a level of service to deliver network packets from a sender to a receiver. When data packets are transmitted from a source to a destination, the route can consist of multiple networks and make use of many network resources. There will always be multiple users transmitting across the network that might overload the network. Some applications transmitting data might be more critical than others and need to get data packets routed quickly and more efficiently. The need for this shared network to provide determined and deterministic priority-based delivery services is even more relevant in real-time applications. In such deterministic delivery services, we demand that both the sender and the network infrastructure have the capability to request, set up, and enforce a delivery of the data packets. It should include a dedicated bandwidth, bounded latency, controlled jitter, and less error rate during the transmission. Collectively, these services are referred to as the bandwidth reservation and quality of service. QoS works by slowing down the lower priority packets and even completely discarding unimportant packets under overloaded network conditions. This leaves room for important packets to flow through the network and reach the destination as quickly as possible. Once the resources along the route from sender to destination are made aware of the importance of packets flowing through the network and also how much data they can queue, then they can act as a traffic shaper by first transmitting the more important packets and delaying less important ones. Different applications have different QoS requirements. Some sample applications include these different kinds of mechanisms and applications. Streaming media might impose quality of service requirements on a guaranteed throughput and low latency, but a more tolerable jitter. Video conferencing or IP telephony, which are real-time applications, might require stricter limits on jitter and maximum delay, but could tolerate errors. For example, if an error is detected, there should not be a need to retransmit the packet and cause some delay problems for future packets. So we just basically tolerate those errors. It might corrupt the sound signal that is received at the other end, but that would be tolerable. Online games where uh, multiple players actually play together across a network need more real-time QoS constraints with bounded latency and jitter, because at this point, if any information is delayed, that would delay the entire game process. A remote surgery, which is a health critical application, might need a guaranteed level of connection availability compared to other requirements. An application that backs up data files does not need any strict bound on throughput or even latency and jitter, but needs to ensure that no error is occurring in transmission. So if an error occurs, you would request a retransmission of the erroneous packet, but you don't care if the rest of the packets are delayed for that reason. Services that require a defined minimum level of bandwidth and can withstand a maximum latency are known as inelastic services. So again, inelastic services are those that require a defined minimum level of bandwidth and can withstand maximum latency. Real-time applications will demand inelastic services from the network. On the other hand, elastic services take advantage of all the bandwidth available to them, however small it might be. An example of an elastic service can be seen in an application that performs data backup. A better categorization of QoS levels are best effort service, differentiated service, and guaranteed service. These services and example protocols to implement them are discussed next. When requirements to provide a certain level of QoS is justified, the sender and receiver typically enter into a contractual agreement with the network providers, which specifies that the network will provide a guaranteed level of throughput, latency, error, and overall performance. This normally mutual agreement by the sender and receiver and the network is achieved by prioritizing traffic flow in favor of the higher quality of service applications on the network. Let's look at best effort service, also called lack of QoS, quality of service. Best effort service, as I said again, is termed as lack of quality of service. Is basically provides basic connectivity with no guarantees or prioritize packets in transit across the network. This is best categorized by first in, first out queuing algorithm, which takes effect when the congestion is experienced. First in, first out does not differentiate between flows, and basically by default is a very simple queuing algorithm on intermediary nodes and routers. It makes no decision based on packet priority, order of arrival, and any buffer allocation, but simply routes each packet in the order of arrival. Packets get dropped in the buffer if the router is full, which is possible when congestion is experienced. Differentiated service also is called soft quality of service. In this model, packets are marked with a priority, which is used to give partial preference while routing of packets at intermediary nodes. The traffic for some packets is therefore different from the rest of them, and the name comes from this differentiated service or different traffic that is experienced by different packets. This provides faster handling and more average bandwidth and lower average loss rate compared with the best effort service, which we have basically discussed before. These servers work by having routers employ various queuing strategies to customize performance according to the um, requirements of priorities. The priorities are set by the packet handlers depending on the protocols that they are using. For example, in the IP protocol that we will discuss a bit later, 6 bits in the header of the packet are used for differentiated services. Different queuing strategies are used to shape and forward packets, and so we will talk about some of these, for example, priority queuing, customized queuing, and weighted fair queuing. In priority queuing, which is a queuing mechanism that is used in the differentiated quality of service, or differentiated service, the incoming packets at the intermediary routing nodes are put into one of 4 queues: high, medium, normal, and low priority. When the router is ready to transmit a packet, it first searches the high queue for a packet. If high queue is empty, it advances to the next medium queue, and so on. And so this is an example here that's shown in this picture. Therefore, priority queuing ensures that important traffic gets the fastest handling at each point where it is being used. Priority queuing is meant to be used on low bandwidth links. The queue sizes or buffers have to be pre-configured and do not adapt to the traffic of the network. The queuing algorithm in custom queuing places incoming packets into one of 17 queues. The first queue holds system messages, such as key fibs, signaling, and so on, and it's basically emptied with weighted priority. The router services the remaining queues 2 through 17 sequentially. At each queue, a pre-configured number of bytes are allowed to be transmitted, and then servicing moves on to the next queue. This feature ensures a guaranteed throughput for all applications by ensuring that no application achieves more than a predetermined portion of the overall capacity. As applications achieve more than a predetermined proportion of overall capacity, basically the queuing mechanism or the policing mechanism moves on to the next level. An example of this application or this kind of queuing is shown in the picture here. Custom queuing also has to be statistically configured like priority queuing and does not automatically adapt to changing network conditions. Okay, the last level of quality of service we talk about is guaranteed service. This is also called hard QoS, or hard quality of service. In this service, packet delivery is guaranteed at any cost. There is an absolute reservation of the network resources that are dedicated to packet delivery. Guaranteed services are provided using resource reservation protocols, or RSVP. And we'll discuss this resource reservation protocol, later when we talk about protocols of the network. This service can be effectively achieved in closed networks. It can be used in larger open band networks that make up different service providers, for example, when you search and browse the internet. But in these cases, core routers would be needed to accept, maintain, and tear down numerous reservations. This behavior does not scale up with the number of nodes and traffic on the network. Deciding which type of service among best effort, differentiated, and guaranteed QoS is appropriate to deploying the network depends on several factors. The application or problem that the customer is trying to resolve or to solve. Each of the 3 types of services is appropriate for certain kinds of application. This does not imply that a customer must migrate to differentiated and then to guaranteed service, although many probably eventually will. A differentiated service or even a best effort service might be appropriate depending on the customer application requirements. The rate at which customers are realistically upgrading their infrastructure is also a big factor in deciding the quality of service. There is a natural upgrade path from the technology needed to provide differentiated service to that needs that provide guaranteed service. It usually is a superset of the differentiated service and therefore needs a better upgrade system, both on hardware and software mechanisms. The cost of implementing and deploying guaranteed service also is a key factor to determine the kinds of service that you might want to use or your customer might want to use. Basically, guaranteed service is much more costly than differentiated service, and so on. Now we have talked so far about different kinds of network architectures for multimedia applications. We talked about the properties of the network, how you can evaluate the performance of your network, and we talked about quality of service. Now is the time to talk about communication standards and protocols for multimedia communications, and that includes our gaming architecture. The requirements for standards in communications are very, very important. During the transmission, the data might be communicated between two end devices, some intermediary routers, data link devices, and physical media. All of these require to be basically in the same subnet and may have different manufacturers. For having an effective communication in this case, well-defined bit streams with appropriate packet headers are necessary so that all involved devices and software interfaces can correctly parse packet traffics and also take necessary actions. The OSI architecture that we started talking about network is a high-level and general-purpose logical abstraction that aims at such standardizations. Specific protocols are further necessary after that level of abstractions to instantiate the abstraction for defined communication requirements. A network protocol is a formal set of conventions, rules, and structures that govern how computers and computing devices exchange data over a network. Many technology vendors and research institutions formalize these protocols over years. And basically, a lot of testing goes into this mechanism. Some of these protocols are basically the protocols that we will be describing in this class. And we group them into two large subsections. One that deals with general purpose protocols and the other that deals with multimedia specific protocols. Which addresses the synchronization, real-time requirements, and other needs that are core to bursty multimedia traffic. Let's first start talking about general-purpose protocols. We first discussed these general-purpose protocols that are used in communication that do not necessarily take care of requirements that are imposed by real-time multimedia, including real-time deployment in gaming technology and gaming network architecture. The first protocol we talk about is the Internet Protocol. The Internet Protocol, or IP, is a network layer protocol that represents the main methodology of communication over the Internet. IP, or Internet Protocol, has two primary responsibilities. Its first responsibility is to provide a connectionless method of data packet delivery, and to do so on a best effort basis. There is no guarantee of data reaching the destination on this level. The second responsibility is to provide fragmentation of large data into packets and its consequent reassembly when the packets traverse the network links with different maximum transmission unit sizes and are received at the end or destination end of your network. For example, the packets might go through an ATM or asynchronous transmission. The IP addressing mechanism is very important and indispensable to how routing occurs in this protocol. Each node on the network is assigned a unique address. It's 32-bit in IP version 4. And this address is divided further into two main parts, a network number and a host number. The network number is a globally decided unique identifier by the Internet Network Information Center, or INTER-NIC. If the network is to be a part of the Internet and the host number is a local number to the network and is decided by a local network administrator either automatically or statistically. So again, we have two parts in the IP address. The first part is a network number. The second is a host number. The network number is globally decided and it's a unique identifier. And the host number is local and is decided by local network administrator, and it can be either automatic or static. When data is communicated from a sender to a receiver, each packet contains both the source and destination IP addresses, which are used to forward the packet. Because of the connectionless nature of the forwarding, packets can arrive via different routes, and consequently they may be arriving out of order. If it is up to a higher level protocol, for example, for a TCP protocol or TCP/IP protocols, to reorder them back together in the correct sequence. The next protocol we will be discussing is called Transmission Control Protocol, or TCP protocol. The TCP is one of the oldest and most robust protocols developed for reliable transmission. It is connection-oriented, and it's also a transport layer protocol, as opposed to IP, which was a network layer protocol. The Transmission Control Protocol, as a transport layer protocol, provides reliable data transfer from a sender to a receiver, regardless of the sizes of the datagram or the packets. Although this packet transmission protocol is connection-oriented, it is normally used in conjunction with a packet-switched connectionless IP, or Internet Protocol. When you combine these two protocols, they form TCP/IP to also reliably deliver data over connectionless networks such as the Internet. For a TCP connection, the sender node and receiver node allocate a buffer called a window, which is used to ensure data delivery. Flow control is established by limiting sending data in the window to the receiver. Once the receiver acknowledges the received data, the window is moved to the next set of bytes in the data. The TCP header contains the source and destination ports, sequencing identifier, acknowledgement identifier, and other fields necessary for transmission and to ensure that the data is reliably received by the receiver. Unlike its counterpart, Universal Datagram Protocol, or UDP, which we will discuss next, the TCP can start immediately sending data. Pardon me, the UDP starts immediately sending data. The TCP requires a connection to be established prior to sending the data, and the connection must be terminated upon the completion of transmission. To establish a connection, TCP uses a three-step agreement to open a TCP connection from a client to a server. The server acknowledges this, and finally the client also acknowledges. This is followed by data transmission. Some of the salient features of data transmission are discussed here. So again, to reiterate the transmission control protocol connection orientedness, let's remember that the TCP needs a connection to be established prior to sending the data, and the connection also must be terminated after the data transmission has been finished. To establish this connection, there are three-step agreements. The TCP opens a connection from client to server, the server acknowledges this connection, and then the client acknowledges the connection. After that, transmission can occur. Every packet in TCP has both the source and destination addresses. This is needed for the source node to know where to send the data and for the receiver node to know where the data was sent so that it could send the acknowledgement back. In order packet reception. So TCP receives packets in order, as I discussed before. Each packet sent by the sender is given a sequence number that is tracked by the receiver and also acknowledged by the receiver by sending an acknowledge message back to the sender. If the sender does not receive an acknowledge message within a predetermined time frame from the receiver, it retransmits the packet, assuming that the packet got lost or dropped en route. This sending and receiving of the acknowledge is done for a group of packets at a time, which lies in the logical window description described previously. Therefore, all sent packets are kept track of and delivery is ensured. Error-free data transfer. In TCP, each packet has a checksum to verify with a high degree of certainty that the packet arrived undamaged, despite any kind of channel interference. If the calculated checksum at the receiver end does not equal to the transmitted packet's checksum, then the packet is dropped and no acknowledgement is going to be sent. So the sender will resend this corrupted package. Discarding duplicate packets. If for some reason a packet is retransmitted because the sender did not receive an acknowledgement or something happened along the way and the receiver receives a duplicate of the packet, this can be detected by the in-order sequence number and discard the duplicate packet. Although TCP ensures reliable transmission, the overhead of retransmitting is normally a hindrance to the maintaining a real-time synchronization for multimedia needs and gaming architectures. Typically, TCP is not preferred for multimedia data communication, and that also includes gaming network architectures. There's another protocol that we'll discuss next that is a counterpart to TCP, and it's more efficient in real-time delivery. It's called User Datagram Protocol, or UDP. UDP, or User Datagram Protocol, or Universal Datagram Protocol, is a connectionless protocol that sends each packet during a session along different routes. UDP does not provide the reliability and in-order data transmission such as TCP does, because data packets might arrive out of order or be dropped by the network, and no acknowledgements are sent by the receiver. However, as a result, UDP is much faster compared with TCP, and it's also efficient for transmission of time-sensitive data, such as the case of synchronization needed for multimedia and gaming data, and is normally a preferred transport protocol for multimedia and gaming networks than TCP. As you can see in the picture below here, UDP is a minimal message-oriented protocol that provides a simple interface between the network layer and the session layer. If any sequencing is needed using UDP, a higher layer such as the application layer has to augment some logic to ensure in-order delivery. The UDP basically is essentially, the header is like as 32 bits. The first 16 bits are the source port. The next 16 bits are the destination port. The data length is the next 16 bits, and the error checksum is the next 16 bits. That's 48 to 63, and the rest of this packet is going to be the data. So as you see here, the UDP packet is a very straightforward, simple packet. A number of communication protocols essentially fall collectively under the category of TCP/IP family. Now remember, IP is a connectionless network layer protocol. TCP was a connection-oriented transmit layer protocol. And UDP was a counterpart of TCP, which basically does not guarantee the in-order or delivery of the packets, and is very useful for essentially the real-time network communications, such as multimedia networks and gaming networks. And the in-order delivery can be taken care of at a higher application, at a higher layer, such as the application layer. So what are the categories of TCP/IP family? The TCP over IP, UDP over IP, and other kinds of protocols in this nature are TCP/IP family. These are the main technical foundations of communication over the internet, and make use of the connectionless packet communication protocols offered by the IP, and augment it with higher level features depending on the needs of the communication. For example, TCP itself is a reliable connection-oriented protocol to transfer data on a network. However, to deliver data on a connectionless internet, it has to ride over the IP, which is a connectionless network protocol, and provide reliability, which is included in order delivery and error-free delivery of the TCP protocol. The TCP family of protocols has the commonality of using IP as a network layer to communicate data while providing support from the higher levels, such as transfer level and layer, application layer, and session layer. The TCP/IP families of protocols include general data transfer protocols such as FTP, HTTP, IMAP, SNMP, SMTP, Telnet, and so on, as well as media-related protocols such as RTP, RTSP, RSVP, STCP, SCTP, and TRIP or TRIP. In this section now, we will talk about media-related protocols, and we enumerate a few commonly used protocols to access and stream media. Apart from the general-purpose protocol requirements, such as those imposed by UDP or TCP, you also have media-related requirements that are imposed by needs such as real-time delivery, resource reservation requirements for guaranteeing of a certain QoS level, identifying the media type that is being communicated, and so on. The first protocol of this kinds of family that we talk about is called Hypertext Transfer Protocol, or HTTP. The HTTP, or Hypertext Transfer Protocol, is an application layer protocol. It provides the swiftness necessary to distribute media information without real-time needs. It has been in use by the www since the early 1990s and has become the de facto standard for transferring World Wide Web documents. In fact, this protocol was invented by Tim Berners-Lee for the web. HTTP works in a request-response manner between a client and a server. The originating client typically is a web browser and runs on a computer, a cell phone, a PDA, or other end terminals. And the client requests a document residing at a server location. The destination server, typically called a web server, responds by locating the document and sending the information back to the client. The information might be individual files or any kind of collection of text, images, and video or audio signals, and any other kind of media organized into the form of an HTML document. HTML stands for Hypertext Markup Language and is used to put and stitch together different kinds of media in one single unified format. The client initiates the request by establishing a TCP connection. The request can go via many intermediary proxy servers, gateways, and tunnels to get to the destination web server. Upon receiving this request, the destination server sends back a response with a header having a status line either HTTP 101.200 OK or an error, followed by a body which is either the requested data file or an error message regarding the data. HTTP defines many methods to initiate and respond between HTTP clients and HTTP servers. Let's discuss some of these HTTP methods. GET. The GET method specifies a request for a particular resource or file. This is the most common type of request method on the internet. HEAD. The HEAD method also specifies a request similar to GET. However, it has no response body. This is useful to retrieve information such as metadata in the response header without having to put up with the overhead to transport all of the contents. The POST method submits user data from the server to the client with the data included as the body of the request. The PUT method uploads the data at the server side. The delete method removes the data wrongly inserted by PUT method. The trace method is used to trace back the received request to the client. This is useful for the client to know how many intermediary servers are adding or changing the request. if any. The options method is used to return the HTTP capabilities of the server back to the client. This is used to check the web server and its functions. The connect method is used by the intermediary proxy servers to tunnel the request through the network to the ultimate destination web server. The next protocol we discuss is called Real-Time Transport Protocol, or TCP. The original IP protocols used on the Internet provided delivery of data packets on the best effort basis. Although this might be enough for non-real-time applications such as email and FTP, it is certainly not suitable for real-time multimedia applications, including the gaming applications. The Real-Time Transport Protocol, or RTP, along with the Monitoring Real-Time Transport Control Protocol, or RTCP, were designed to solve real-time needs of multimedia traffic, such as video and audio streams in applications, video on demand, video conferencing, and other live streaming media. RTP was originally designed for multicast and support distribution to multiple networks. RTP runs on top of the UDP, or User Datagram Protocol, or Universal Datagram Protocol, rather than on TCP, because TCP's reliability achieved by in-order delivery of packets does not address the real-time needs of multimedia traffic if packets are lost or received erroneously. UDP, on the other hand, delivers packets without any heed to order. Though this is desirable, it does create problems when packets arrive out of order and are destroyed, and also when the synchronization stream is not kept intact. RTP must create its own timestamping on each packet and its own sequencing mechanism to help receive synchronization or data in a synchronized manner. To achieve synchronization in RTP, the following parameters are added to the protocol. Payload identifier. The payload identifier, which refers to the packetized data, needs to be supplied with an identifier indicating the media type it contains as well as the encoding scheme. This helps the receiver in appropriately funneling data to the appropriate decoder and processing units when the application contains many different media streams, such as audio, video, image, and so forth. The timespan records the timing information necessary to decode and play media data in a proper timing order. So this takes care of in-order delivery or out-of-order delivery in UDP. Depending on the standardized compressed stream that is being used, this can also include either or both of the DTS, decode timestamp, and CTS, composition timestamp. Timestamp information is set by the sender depending on the information obtained by a higher level layer, and helps not only intermedia, such as playing video at a proper frame rate, but also intermedia synchronization, such as playing video and audio at the same time. The sequence number is used to supplement the timestamp information. This is incremented by 1 for each RTP data packet sent, allowing the receiver to reconstruct the packets in the sender's original order when they arrive out of sequence. SSRCID is a sequential source identifier and basically suggests the dependencies of multiple media streams that are being sent by the sender and need to be synchronized. Audio and video streams are common examples. Optional CSRCID basically identifies contributing resources, such as multiple cameras providing different streams of video conferencing and so forth. An example of an RTP packet header incorporating this information is shown in this picture. Along with RTP, the RTCP supporting protocol control and maintain the quality of service. RTCP works by initially creating a channel connection between the sender and receiver and monitoring the data transmission and conveying information to the sender. Although the data packets sent by RTP and RTCP belong to the same session, they go to different ports at the same IP address. Real-time streaming Protocol, or RTSP, was developed by the Internet Engineering Task Force (IETF) in 1998 and is useful in streaming multimedia as opposed to downloading the entire media content. In the fleeting days, when bandwidths were low, the only option to transmit multimedia data was to download the entire content at the receiver end and then play them, or have the receiver node set aside a buffer that, when filled to a certain extent, would allow uninterrupted playback. The buffer space required here can be large if a smooth playback is desired in the presence of low bandwidth or jitter in the network. Now, with the broadband connections and higher compression standards, multimedia data can be viewed almost instantaneously by streaming of the data. RTSP is designed for streaming communication between a client and a stored media server and achieves real-time communication by issuing simple commands like play, pause, stop, and so on. Therefore, it allows time-based access to files on a server. RTSP normally rides on top of RTP as a transport protocol for actual audio-video data. RTSP requests, which are sent over HTTP, include the following. A describe request is sent to a server address, normally an RTSP URL, to obtain the presentation descriptions such as media stream type, like video, audio, graphics, and other particular pertaining to the media, such as image size, frame rate, compression, codec, and so on. A setup request sent by a client imposes a transport protocol to communicate the media stream data, for instance, an RTP or RTCP. The setup requests also include the port number for the transported media to be delivered. This has to be done prior to requesting the data and delivering any media information. The server usually follows a response confirmation, basically confirming the chosen parameters, and will fill any unspecified information in the request to standardize default values. For example, receiving port number can be put in if it's not specified. After setup and during a session, the client periodically sends an RTCP packet to the server to provide feedback information on the current quality of service in the progress. Play is a request that's caused by the media stream from the stored server to be delivered to the client for playing. Pause request basically temporarily stops the delivery of the multimedia streams, so it can be resumed at a later time by another play request. The record request allows media stream data to be sent from the client to the server for storage. Fast forward and rewind request, also as the name suggests, move the media state forward or backward in time. And teardown request terminates the real-time session that was established between the client and multimedia server and frees all session-related data and resources from the server. An example of an RTSP connection is described here. The sessions start with describe and setup commands, and once play is requested, multimedia data is delivered using the RTP protocol. The session is ended then by the teardown request. And in the meantime, you could basically have stop requests, fast forward requests, and rewind requests. The Resource Reservation Setup Protocol, or RSVP, is a setup protocol where a receiver node reserves network resources during the communication session so as to efficiently monitor and guarantee the desired quality of service for unicast and multicast multimedia communication over an integrated services internet. The protocol defined previously, although they might monitor quality of service, such as in RTP, they do not specifically address control and rectification of quality of service issues. RSVP works by applying two messages, a path message and a res or reservation message. A path message is initiated by the sender to the receivers and contains information of the path and nodes along the path to the receiver. This follows by one or more reservation messages from the receiver to the sender, the intermediary node resources. Some of the main features of RSVP can be categorized as follows. RSVP requests resources for traffic streams in only one direction, from sender to one or more receiver. There can be multiple senders as well, depending on how the application chooses to broadcast. The RSVP is not a routing protocol, but works with the routing protocols to transmit data along allocated resources, which might be routers by themselves. In RSVP, the receiver in a transmission flow initiates and maintains the resource reservation for that flow by making RSVP a receiver-oriented protocol. A reservation might merge with an existing reservation with two receivers attempt to serve the same resources, for instance a router for the same session in a multimedia distribution. The merged reservation has to maintain the highest quality of service needs among all merged reservations. RSVP maintains a soft reservation state for each resource, meaning the reservation at each node needs a periodic refresh from the receiver host. This is necessary for two reasons. One is to automatically adapt to dynamic changes in the network when nodes go offline or routes are dismantled. And the second reason is to control and distribute the bandwidth so that one reserved node does not use up neighboring bandwidths. RSVP provides various flavors or styles to allocate intermediate resources. These might fit different application quality of service requirements and can also be extended as per need. An example of an RSVP process is shown in this figure. Sender 1 and Sender 2 send path messages to Receiver 1 and Receiver 2 on the left and right. Receiver 1 sends a reserved message along the received path back to Sender 1. And this is basically what is shown in the image in the middle. Receiver 2 sends a reserved message along the received path back to Sender 2, which is shown on the second or the right-hand side image. Both the path messages can be merged at an intermediary node, which is the node at the bottom here. The next protocol we talk about is Session Initiation Protocol. The Session Initiation Protocol is an application layer protocol, control protocol, such as HTTP, that has been set up to establish, modify, and terminate sessions in the Internet telephone. Although designed for voice over IP application, it is not limited to voice over IP or VoIP applications, and is also used for multimedia-related communications, such as video conferencing, multimedia distribution, and so forth. This protocol may be the protocol that is used over the multiplayer role-playing games, massively multiplayer role-playing games that incorporate voice commands and voice chat. SIP transparently supports name mapping and redirection, which increases personal mobility so users can maintain an external visible identifier regardless of their network location. The SIP is a client-server protocol where the sender client node connects to another receiver client node in a multimedia application by initiating a request to a server or multiple servers. The servers responds by the address forwarding that ultimately reaches the receiver client. There are three types of servers: proxy servers, their job is to forward the client's call request; redirect server, whose job is to return the address of the next hop server; and location server, which finds the current location of the clients. The clients can invoke the following commands. Invite is invoked by a client caller to get another client or other clients as callees to participate. Acknowledgement is invoked by client or callees to acknowledge an invitation. Options is invoked by client to inquire about media capability without establishing a session or a call. Buy is invoked by a client, either the caller or the callee, to terminate the session. Register is invoked by clients, either caller or callees, to send a user's location to the SIP server. An example of the SIP session in process is illustrated in this picture. The caller and callee clients are registered on the network user proxy servers. So SIP client caller is on the server, the client computer at the upper left side, and the SIP client callee is at the bottom right side, and their proxy servers register these users. The client caller can reach another client to be called by tracing the registered location through the network. The sequence traces of the invite message originating from the caller client are shown numbered in black, and the acknowledged message responses are generated by the callee clients are shown in the gray numbered links. So the caller sends a response or an invite message, goes to the proxy server. The proxy server looks up the location server, goes back to the proxy server, goes to the second proxy server, goes to the redirect server, goes to the next proxy server that contains the client callee, and goes to the callee. The acknowledgements are sent back on the trace. Notice that the proxy server connected to the client caller does not need the acknowledgement to be sent over the location server anymore. Now here I'll talk about the session description protocol and telephone routing over IP protocols just real quickly, and if you are interested in these protocols, you can check out the PDF file and learn more about these. The session description protocol describes a multimedia session that needs to be in session between a caller client and a callee client. A caller client must include this information when inviting the callee during the initiation of the communication. The description information includes the media stream types used in the session, video, audio, and so on, and its capabilities, destination addresses, for example, unicast or multicast for each stream, sending and receiving port numbers, stream type indicators, and other things necessary to communicate media. When a caller client sends the SDP information in the invite message, the callee client can choose to change it to fit its communication expectations. The TRIP, TRIP, or the Internet Telephony and Voice over IP, is basically a routing mechanism over the Internet protocol, and it's an administrative domain protocol that helps clients reach destinations between location server or multiple location servers. The primary function of the TRIP client, called the location server, is to exchange information with other location servers. The information includes the reliability of or reachability of telephony destination, information about intermediate gateways, and routing information. Also, TRIP can be used to exchange attributes necessary to select correct routes based on gateway attributes. This is used to define synchronization and transport methodologies for the communication. TRIP's operation is independent of any particular telephony signaling protocol, such as H.323 or SIP, and therefore can be used as routing protocols or any of the signaling protocols. TRIP runs over a reliable transport layer protocol like TCP or UDP, and therefore does not need any support for error correction, packet defragmentation, and so forth. So this basically concludes our overview of multimedia networking architecture. And at this point, you should have your memories refreshed about what networking is, how different issues in networking are handled, and some of the architecture and protocols that are used in the networking in general, and multimedia and game networking in particular, that we discussed in the last 3 weeks. So with this, in the next unit, we will look at primarily web-based game network architecture and look at how we can use the server that we are basically working with in this class, the Electro server. Thank you very much.